Hello and welcome back. In this series of lectures, we will look at semantic segmentation and fully convolutional networks that are used for accomplishing this task. So let's consider this image here. It's an image of a building. So if you have a typical look, if you consider the neural networks that we have looked at so far, especially those that have done well on the image recognition challenge, and if a building is one of the classes, what the network would typically do is to just identify this image as a building, or for that matter, a lawn, or let's say a skyline, for instance. However, in many tasks, what is required is actually a pixel-wise labeling of the scene. So if you see on the right here, this is the result of a semantic segmentation network shown here. So it has classified each of the pixels into a corresponding category. So for instance, this region here, it's a building. So this region, all the pixels in this region have been classified as a building. The skyline is appropriately classified as skies, and we have the vegetation here, and the fencing is also being classified accurately. Of course, there are some errors where it mistakes the shrubs for the fencing also, but that is to be expected in some networks. So this is the typical task that we would like to accomplish in semantic segmentation. That is basically classify each pixel as belonging to a particular category. There are many nuances here. So for instance, if you look, there's just one building. Let's say there are a series of buildings separated by some space, and in some applications it is actually desirable to label each of those buildings and also recognize them as being individual buildings. So this is called instant segmentation. It's slightly more fine-grained task than what we are going to look at right now. The applications we are going to look at, the networks we are going to look at, will only segment objects of a particular type. So if we say if there are multiple buildings, they will all be designated as buildings. If there are multiple objects of the same type, they'll be just designated as an object, okay, of the same object. So for instance, so just to reiterate, we want to classify every pixel as belonging to a particular object, and that should be the output of the network. Okay. So how would you accomplish this with, let's say, some of the networks that we have seen so far, with a regular conventional CNN that we have looked at so far in these lectures? So for instance, take this input, same scene of a building surrounded by lawns. So what we typically do is take patches of certain sizes, let's say 64 by 64 patches, and give them as input to the convolutional neural network to classify it as belonging to one of n classes. So for instance, we might train a neural network to identify sky, vegetation, buildings, and objects, general objects, or person, and you train the network as such. So for instance, the ImageNet challenge had 1000 categories. So we can use a similar network, train a network similarly to identify any of, let's say, 4 or 5 categories, depending on the kind of scenes you are looking at. So for instance, images of parking lots, we just want to classify driveways and cars and maybe signs. Okay. So the idea is to take patches from the image, pass it through the network, let's say a typical CNN, and output a particular class, the probability of the particular class, or the score for the particular class. So that way we will accumulate. So this score is for the center pixel of that patch. So that's what is shown here. So we would slide the patch, center the patch around every pixel in the image, and classify that particular pixel as belonging to a particular category. So as you can see, this can lead to a lot of computational overheads, because typical images will be of the order of 200 to 500, about a million pixels. So we'll have to do a million forward passes through the network in order to label every one of the pixels. Of course, you can subsample the image and do it, but that will lead to errors in the semantic segmentation. So the issues, as we stated earlier, it's very inefficient in terms of computations, and there is no feature sharing among the overlapping patches, in the sense that the network only looks at that particular patch and it does not pay attention to what is around that. So ideally, to make it more effective, you would end up taking larger and larger patches, which of course would mean that you would end up doing more computations, and the results will take a longer time to be output. So what would we ideally want? Okay, so that's where we are now slowly moving into this fully convolutional neural network. We'll see what that is in a few moments. What would we ideally want? We want an input image, let's say of size h cross w, with 3 channels. This is a typical RGB image, and we would like to send the image through a series of convolutions and have an output layer which has as many feature maps as there are objects that we want to detect, and each of those feature maps correspond to a score which gives the probability that a particular pixel in that map corresponds to a particular object. So in the end, we take the argmax across the feature maps and assign labels to every pixel in the input image. So this is typically what we would like to accomplish, because this would be more efficient. And another advantage would be, since if we make it convolutional, as we see here, we have left out max pooling layers and all that, and as it's convolutional, we can give inputs of any size. Okay, that's another advantage. So we don't have to be restricted to a fixed size image. So if you looked at the method we explored in the previous slides, it's basically you have a CNN which takes as input a particular size patch, and then it classifies the center pixel. Here there will be no such restrictions. That is typically what we would want, and this is the aim for the fully convolutional network. Now, if you look at the, so let's just go a little bit in more detail as to how these things work. Okay, so what we want is, if we have an input image, a typical classification network is what we want to use for semantic segmentation. So you would take patches from the input image and feed it to the CNN. Again, this is AlexNet shown here, alternative convolution and max pooling layers. However, what we do see here at this layer here, the 3x3 pooling layer, followed by a fully connected layer. KFC is fully connected layer. Here, what happens is, here after max pooling, its size is size would be 256 cross 7 cross 7. Okay. That would be the size of the volume after max pooling. Now this is fully connected to the 4096 neurons. So in order to do that, we have to rasterize it. So 256 cross 7 cross 7 is rasterized into one vector and is fully connected to the next layer, which has 4096 outputs. Okay, so this is what prevents us from having an arbitrary sized input. Okay, because if we have, let's say, a slightly larger input, then this would be difficult to do, because the number of weights here are fixed, right? So how many weights are there? So if we calculate 256 cross 7 cross 7 times 4096. So this weight matrix is the size of the weight matrix, number of elements in the weight matrix, right? Now if we have, let's say, a larger image, 224 cross let's say 400 cross 400, and what happens here is that this feature map size would increase right here. This number would be much larger. The size of the feature map would increase. Number of channels would be the same. Size of the feature maps would increase, but then it's not possible to propagate beyond this point because the number of weights are fixed here. Okay, so this is a restriction that comes in with whatever networks we have looked at so far, is that size of the input has to be fixed. So we can't use arbitrary input sizes, right? So we, in order to have a very flexible semantic segmentation framework, we would like to have a network which does not have this limitation. So what we do is to convert these fully connected layers into what are called fully convolutional layers. So how do we go about doing that? So let's just take this typical block of input coming into a fully connected layer, right? So this has 7 cross 7 feature maps, 512 of them. 7 cross 7 feature maps, about 512 of them, and we rasterize this and fully connected to 4096 neurons, which in turn are again fully connected to 4096 neurons. And then we have, let's say, this was like AlexNet. We will have these would be connected to 1000 output classes, right? Softmax, 1000 way softmax if you want. So how do we convert this into a fully convolutional layer? Okay, so we would, not to accomplish that, we would just define filter kernels that cover the entire input region, right? So for instance, we can define 512 filters, or excuse me, So in order to convert this particular layer into a fully convolutional layer, what we would do is define 7 cross 7 filters. Of course, the depth of the filter is 512. We will define 4096 of them. Okay. So this will lead to 4096 1 cross 1 feature maps. And then in turn, we will again define 4096 1 cross 1 filters whose depth is again 4096, and we will get 4096 outputs. Okay. So this is how one would convert a fully connected network to a fully convolutional. That is, to just before the fully connected layers, you define filters which should cover the entire input region, and then the fully connected regions themselves, you would convert them into 1 cross 1 convolutional layers. So that now the network is fully convolutional. So what advantage does it produce? So let's say for this particular network, we have an input that's coming in which has 22 cross. This particular layer gets a larger input. Let's say because your input size is different. It's 22 cross and 512 channels. So you can see that since we have defined 7 cross 7 filters, you will get a 16 cross 16 output. Again, the number of channels is fixed, 4096. And again, by doing 1 cross 1 convolution, you get 16 cross 16 output feature maps. Okay. So once this is accomplished, now we have to see how we can use this for semantic segmentation. So what do these feature maps represent? And in fact, do they represent anything at all? And how we would get to the point where we can do semantic segmentation. So let's see how see the difference between image recognition and after fully convolutionalization. What does the outputs mean? Okay. So for an image recognition network shown right here, you would have as input an image, and in this case, what we have shown is a sequence of convolutional layers, and these are the fully connected ones right here, 4096, 4096 and 1000 output classes. So these are the fully connected layers. So you would get 1000 output probabilities or scores, and you would assign the label corresponding to the highest probability. So in this case, the highest probability corresponds to cat, so you would call it a cat. Now let's say we have an image. In this case, we have now a fully convolutionalized neural network like we saw earlier. So instead of going from the 256 to the fully convolutional fully connected layer, we define filters which span the area of the input volume. Okay. So then once you have done that, then if we have a slightly larger image as shown here as input, then we would get again 4096 feature maps of a given size, and each of these we can again do a convolutional layer to give rise to 1000 feature maps, 1000 output maps, and if you look at one particular map there, so these are feature maps, these two feature maps, 4096 feature maps of particular size depending on your convolutional kernel, and we have these 1000. So these 1000 output scores. Now previously in the conventional CNN, these were just 1000, a single vector of size 1000, but in this case there will be 1000 what you call activation maps or score maps. Each of these 1000 outputs is itself like a feature map or a map which contains the probabilities assigned to every pixel. So if we take a slice of this 1000 and look at it, this is what is shown here. It will be like in an image wherein the values show the probability of every pixel being a cat. Okay. So this is how by converting from an image recognition fully connected image recognition network to a fully convolutional network, the output scores themselves are like images, with the pixel values of those images being the probability of that particular class. So the nth map will correspond to cat, and if you pull that out and look at and inspect the values, it will show you that each of these would correspond to the probability of that pixel being a cat. Okay, so now we have, for an input image, we have a slightly, so if you look, this image is smaller than the input image, so we have a slightly coarser or a subsampled version of your probability scores. Okay, so this is what, so this is the problem that we will address. So we know that because of the subsequent sequence of layers of subsampling present in a typical network, the output score map will not be the same size as the input image, so it will be a subsampled version. So the probabilities that are produced are also coarse. So of course the most logical thing to do would be to upsample this by interpolation. So you can upsample this to get the same size as the input, with the every pixel showing the probability of the class. So how do we actually accomplish that, this subsampling? That is the question, right? So we have, so once again, we have this typical image recognition network, and by turning the fully connected layers into convolutional layers, we obtain 1000 score maps corresponding to, let's say, we are dealing with ImageNet data, so it's okay to, let's consider 1000 categories. So 1000 score maps, and but then these maps are coarse. What I mean by coarse is that the size of the, it's much smaller than the size of the input image, right? So if the input, so what we want to do ideally then is to upsample this to get to input size, right? So the simplest way, as I mentioned earlier, is to do bilinear interpolation. You don't have to learn it. In fact, you can have a learnable bilinear interpolation, but that's not very efficient because in the process of downsampling throughout this network, you have lost some information. So one of the earliest papers, papers to do fully convolutional networks for semantic segmentation, what they did was to pick out feature maps from the intermediate layers and add that to the output. So how is that accomplished? So for instance, let's consider the feature maps from this 3x3. Okay, so they are of a particular resolution, right? You can work out the exact numbers on your own, but just for the sake of illustration, we can also pull out feature maps from this particular layer. They are of a particular resolution, right? So, and then we have the output from here, which again is of a particular resolution, let's say, right? So the idea is to upsample each of them and add. Okay, so what that accomplishes is that, so the resolution you have lost by going deeper into the network, we are trying to reclaim. So how does this, so but then we'll have multiple feature maps as the output of a 3x3 pooling operation. So the way to do that is you would do 1x1, again 1x1 convolution to get one feature map, and then you would do bilinear upsample all of them, and add. This upsampling can be learnt. Okay, so this is what we saw as transpose convolutions in earlier lectures. That's what it enables, is by upsampling feature maps from the earlier layers following a max pooling and adding it to the output layer. Again, we still have to, the output feature map, these 1000 output score maps are actually quite coarse, so we still have to upsample them a bit in order to match the resolutions of the feature maps from the earlier layers. But we add them and produce one score, and we do a pixel wise cost function. So your loss function would be summation over the pixels in the output score maps, and summation over the number of elements in a number of samples in a mini batch. So, and then of course back propagation is the same as earlier. Since we are using transpose convolutions, again it's just that the operations is inversed, but still the back propagation algorithm will work seamlessly. So that was one of the earlier techniques that was used. But following that, another technique that was proposed, and it's now very popular, it's very similar to that what we saw earlier by pulling feature maps from the earlier layers, which is, again, we can call them skip connections or shortcut connections. Okay, and those seem to work. However, the recent past, the most common architecture is the encoder-decoder network. So how this works is basically we have an encoder series of convolutions and max pooling layers, and after we reached a specific size of feature map, we would once again do a decoder. These are again a series of convolutions and max unpooling, as it's called. If you do that, to get a feature map of the output scores would be of the same size as the input. Okay, so the idea behind the encoding layer is to extract the most relevant features from your input, and the decoding uses that to produce a pixel wise labeling of your input. So this encoder decoder structure is what is typically used for semantic segmentation. The advantage here is that, as you can see, there are these we'll look at what these are, but there are these connections which take input from the earlier layers in the network and then pass them on to the corresponding layers in the decoder. So you can see that there is a symmetry between the encoder and decoder. We'll have similar sequence of convolution and max pooling in the decoder as well as the encoder side. You can say that the decoder side is a transpose of the encoder. Okay, so here in this particular network, this uses a technique called max unpooling. Which eliminates the need for upsampling. Okay, needs for learning to upsample. So you saw in the previous slides, the technique we looked at was it has to learn to upsample the final output score maps, as well as to upsample the feature maps from the earlier layers in the network so as to match the input. So there is some learning required. Here they get over it by doing something called max pooling. So how does max unpooling? How does max unpooling work? So here, let's say this is a feature map. It's just a toy example, size 4x4. So if you do a 2x2 max pooling of size 2 cross 2, then in every block here, the red block here gives you 9, and the green block here gives you 8. Here it's 15 and 10. So those are recorded, and this is your pooled feature map. However, while doing that, we also keep track of the indices. So if you raster it, so for instance 9 would be if you 1, 1, that's what this is, 1, 1, 0, 0, 1, in each of the sub blocks, right? So for instance here this is 1, 1 in this 2x2 matrix, this is 0, 0 in this 2x2 matrix, and 10 is 0, 1 in this 2x2 matrix, and if you say 15 is 1, 1 in this 2x2 matrix. Okay. So if you take track of this index, now we come to the unpooling layer. So where is the unpooling layer? The unpooling layer is on the decoder side, where the feature maps are of the same size. When you come to the unpooling layer side, then you would make this larger feature map array and assign the values to the corresponding locations. Okay, so for instance, you will have a sequence of convolutions on the encoder, on the decoder side. Following the convolution, you will have a max unpooling. So you take the output of the convolution. So this is the output of the convolution, and assign it to a larger array to the array with corresponding to the indices shown here. Okay. So by keeping track of the max pooling indices, you should be able to construct this matrix by assigning the values. Here, just for the sake of illustration, I have just taken taken the values from a 4x4 and assigned it to another 4x4 to do something similar, but we have to keep track of the indices here. Okay. So now once the max unpooling is done, in this case by assigning the values to the larger matrix as indicated, we can then proceed to do convolutions. The convolution kernels, convolutions are done as in a usual conventional neural network, and of course the network learns to fill in the activations appropriately. Another architecture which is again found wide applications in biomedical image segmentation tasks is called the UNet. Okay. So this network again is very simple, similar. So you have in this case the encoder and the decoder side here, and we have these skip connections between the encoder and decoder. Okay. This particular network again does transpose convolution, so it does learn the upsampling, but it does go deeper than most networks, and because of the skip connections, generally the outputs are of a much higher quality. So let's start with, let's say, a typical input of size 512 by 512. Here I have shown an image of cardiac MRI slice, size 512 by 512. So you would produce 64 feature maps, a succession of 2 convolutions to produce 64 feature maps with padded convolutions so that the size is retained. Here throughout this network, similar to VGG, we do 3x3 convolutions. Okay. So this red indicates max pooling. So your 512 cross 512 will become 256 cross 256. Number of channels remain the same. Once again, you will do a sequence of 3x3 convolutions to produce, again similar to VGG, you have 128 feature maps. The initial layer was 64, we have 128, and then followed by max pooling. Okay, and then 3x3, again we will do 3x3 convolutions to provide 256 feature maps. There is a max pooling layer there which gives you 64 size feature maps, and then once again do convolution to produce 512 feature maps, two successive convolutions, and then followed by a max pooling layer. So you can go across this network. I've just shown you on one side on the encoder size. So on the decoder side, again you would exactly duplicate this operation, but then instead of convolution instead of the max pooling, you will do the upsampling. So here it's max pooling on this side. On the encoder side, you will do upsampling. Again, the convolutions are again the same as 3x3 convolutions, and you would systematically reduce the number of feature maps as you go towards the output side. In between, you would copy. In between, for instance, as shown here, these gray lines show that you would take these feature maps from the encoder side and concatenate them to the decoder side. Again, here there are multiple options. You can concatenate. Here it's shown as concatenation, or you can do a RESTnet like processing where you can just add them. That's also possible. And if the number of feature maps begins too difficult to handle, then you can just do a 1x1 convolution, reduce them and add or concatenate to the encoder side. So as you go up the encoder, one of the things you have to notice is that you would take feature maps from the decoder side at the same resolution and add it to the you would take feature maps at the same resolution from the encoder side and add it to the decoder side. This is very similar as to what we saw with the fully convolutional networks. And the first fully convolutional network that we saw is we take networks from feature maps from earlier in the earlier layers and add them to the output. So this is done more systematically here. So again, at every layer in the decoder side, you would go and find a corresponding feature map of the same size, of the same resolution, and add it. In this case, you can do a RESTnet like residual connection, or you can just concatenate one cross one convolutions can also be done to shrink the size of the feature map so that you don't have a feature map explosion on the decoder side. And finally, you would produce an output with a requisite number of classes. So you would do convolutions so that the number of channels, for instance, if you are looking at 5 classes, the output will have 5 channels of output, with each channel corresponding to a particular category and the pixel values in that channel representing the probability of that particular class at that pixel value. So this is the very often used network for biomedical segmentation tasks. We look at an application where this can be used later on in the next few weeks. Of course, we have also seen dense nets. So what we saw, we can do similar processing with dense nets. So instead of having these VGG-like convolution blocks, all you have to do is replace the convolution blocks with a dense block. And instead of max pooling, we have the transition blocks. As we seen earlier when we were discussing dense net, we use the transition down blocks to bring down the resolution on the encoder size. Similarly, we have transition up blocks on the decoder size to improve the resolution. So which is same thing like we do deconvolutions or transpose convolutions as they are called. Deconvolution is apparently a wrong nomenclature because deconvolution is well defined in electrical engineering. So transpose convolutions are more appropriate terminology to be used. So the only difference between this network and the one we saw earlier in UNet is that the VGG type convolution blocks are replaced by dense blocks. So this particular architecture, which is basically the encoder and decoder, the idea is we can use any of the networks topologies we saw, architectures that we saw which were used for the ImageNet challenge. But of course, the only thing we have to do is on the decoder side, we have to formulate the appropriate channels or the architecture. So, for instance, this is just to illustrate again. If you go back to the UNet architecture, we'll see that this is basically this is nothing but your this particular whole thing is nothing but your VGG type block. Okay, so we have 264, 128 here, and then we have 256, and then 512, so on and so forth. Of course, VGG had 3 512s blocks, but we can have a VGG or AlexNet on the encoder side, and then we just have to flip that on the decoder side. Of course, it's no guarantee that all of the net architectures would work. This particular architecture actually works. You know that for sure. They have been published and applied to many image processing tasks. The next series of lectures, in the next series of lectures, we will consider transfer learning. Again, we'll see how we can use these pre-trained networks to and apply them for related tasks, and how that will, in the case there is not enough data. And also followed by that, we will also look at hyperparameter optimization.